Okay, this is Dr. E. Back again to talk about energy. In earlier video lessons, we talked about how energy is needed to do work, or energy is the ability to do work. We talked about certain forms of energy that can be interconverted. In particular, we talked about potential energy and how it can be converted to kinetic energy. Potential energy being stored energy. And one form of potential energy that is easy for us to visualize would be the energy stored in an object if it's lifted above the floor. For example, if we lift a 50 kilogram weight above the floor, it has stored energy, potential energy. If we drop it, that potential energy is converted to kinetic energy. In this video lesson, we'll talk about this third important concept. The total amount of energy in an isolated system is conserved. And we'll talk in particular about what is called the first law of thermodynamics. It sounds important. The first law of thermodynamics. Beat me. Hurt me. Teach me thermo. Thermodynamics. The study, sometimes painful, of energy, heat, entropy, and work. So in this video lesson, we will take a right cross on the chin and talk about the first law of thermodynamics. Before going there, let's go back and talk about thermal energy, which is also called heat. We mentioned thermal energy or heat a couple of times in the last lesson. We talked about the bungee cord in which potential energy is converted to kinetic energy, back and forth, and eventually it would all be dissipated, and we said dissipated as heat. We also talked about James Watt and how he was an important developer of the steam engine, how this relies on heat. And it was important for Watt and other scientists to understand heat to try to maximize the efficiency of the steam engine. How is heat produced? Well, we know that heat can be produced in a number of ways. You can produce heat by burning wood or coal or oil, fire. By rubbing two objects together to produce heat through friction. Passing electrical current through a wire produces heat, or through a heating element in our electric range. And we're of course familiar with the concepts of hot and cold. But what does all this mean? What does it mean for something to be hot and something to be cold? Well, heat was a vexing form of energy because it's not easily seen. Now, sometimes it can be seen. If you take a metal poker and place one end into a fire, it can be heated up until it's red hot, and when it's red hot, it's obvious to us that it's hot. It's at a higher temperature. And hopefully we're holding the other end with a glove, and we know that over time, that heat, that thermal energy, will flow from the hot end to the cold end. Okay, so for some time, scientists conceived heat as being some kind of internal, invisible fluid within substances. A fluid that would flow from the hot end of an object to the cold end. And in fact, they called this fluid caloric, and it's the origin of the term calorie that we use today. So heat flows from hotter to colder. Let's consider this experiment. Imagine that you're a blacksmith, okay, and that you've heated up a horseshoe in a forge until it's red hot, a thing blacksmiths do, and you drop this into a bucket of room temperature water. What will happen? Well, you can imagine that thermal energy will flow from the hot horseshoe, the red hot horseshoe, into the water. Thermal energy, which we call heat, sometimes we abbreviate that as Q, will flow from the horseshoe to water until they both reach the same final temperature. A fairly common observation, but a very important observation, because thermal energy does not flow in the opposite direction. What do I mean by that? Imagine after you have this horseshoe in the bucket of water and it's reached a final temperature, maybe it's now a little above room temperature, you reach in with the tongs and pull out the horseshoe. That horseshoe is not glowing hot. with the water now being lower in temperature. That is, that thermal energy does not separate itself into a hotter object and a colder object. Instead, it flows from hot to cold to reach an equilibrium or an equalized temperature. An important concept. We'll talk more about that in the next chapter on the second law of thermodynamics. But for this chapter, it's important for us to know that thermal energy is associated with the movement and vibrations of molecules in a substance. That is, the Jameses, James Watt, James Prescott Joule, and other scientists over time extended this caloric concept, this invisible fluid, to our current understanding, which is in terms of molecules, the vibration and motion of molecules in a substance. And that is actually what constitutes thermal energy. Now, we can't see the motion of molecules because they're too small. We may be able to feel or sense something that's hot, either by seeing it glowing red hot, or sometimes we place our hand next to an object and we can feel the convection of air. You know, also, I have young grandchildren, that one of the first things we teach our children is to avoid something that's hot. One of the first words they learn is hot. Why do we teach children that? Because it's not always easy to tell by looking when something is hot and something is not hot. Imagine 2 glasses of water, one at 5 degrees centigrade, cold, and one at 50 degrees centigrade, warm. They look pretty much the same. But which one has the most thermal energy? Right. The one at 50 degrees centigrade possesses much more thermal energy than the one at 5 degrees centigrade. Now, thermal energy, we will learn in the next chapter, depends not only on temperature, but also on the amount of a substance and also on the identity of a substance. But more on that later. Let's now talk about this first law of thermodynamics. The laws of thermodynamics are very important to understand because energy is essential in our lives and in understanding nature. And scientists realize that these laws govern energy. The first law. I thought I heard a drum roll. The first law. In an isolated system, the total amount of energy, including heat, is conserved. Say that again. In an isolated system, the total amount of energy, including heat, is conserved. Now, this can also be expressed in the following way. Energy can be neither created nor destroyed. Energy is neither created nor destroyed. That is, this first law is a conservation law, like the law of conservation of matter. This is the law of conservation of energy. Energy is neither created nor destroyed. Now back to this statement of the first law. It uses common words, but it turns out these words have important meaning. What does it mean to say an isolated system? Okay, let's explain that in this slide. What is a system? A system refers to the matter that is under consideration. Okay, imagine having a box or a test tube. What is inside this box or test tube is inside the system. What is outside the box or test tube is the surrounding. Simple enough, right? And this system can then be either open, closed, or isolated. And the isolated system is the one used in the definition. So, an open system, if you look at the drawings at the bottom of the slide, an open system might be a test tube without a lid on it, or a box open at the top, where both matter and energy can be exchanged between the insides and the outside, the inside of the system and the outside of the system. It's like having a house with the doors and the windows open, and the dogs and the cats and the light and the heat can go in and out. A closed system, we have a lid on it. A lid on our test tube, we have the lid on our box closed, we have our windows and doors closed, so that matter cannot flow between the system and the surroundings, but energy in the form of heat or light, like sunlight going through windows or through the glass wall of this test tube, that energy can go in and out between the system and the surrounding. Okay, then an isolated system is one where we have both a lid on it and we've surrounded the container with insulation such as styrofoam so that neither matter nor energy can flow between the insides within the system and the outside, the surroundings. So that's what we mean by an isolated system. It's all snug inside of this system. So under the latter condition, isolated system, the first law says again that energy can be interconverted between forms. That is, potential energy can be converted to kinetic energy, or potential energy to electrical energy, or potential energy to heat, but that it all has to stay within the system. The total amount of energy is conserved. It might be degraded to heat, but the total amount of energy remains the same. Now, this first law also says that in an isolated system, energy cannot be created from scratch. In the next chapter, we'll talk about the second law, and we will learn that any mechanical, chemical, or biological system cannot be 100% efficient in converting energy from one form to another, in the sense that there will always be a degradation of energy, such as friction, degrading that energy to heat. But more on that later. So, the first law says, you remember it, in an isolated system, the total amount of energy, including thermal energy or heat, is conserved. That is the right cross of the first law of thermodynamics. And later we'll get the left hook, the second law of thermodynamics, and learn about entropy. Okay? So we pause now, have a little quiz, and in the next video lesson, we'll talk about engines. Engines are what we use to convert stored energy, such as chemical energy and fossil fuel, to perform mechanical work, to move down the road. And so we'll talk about internal combustion engines and the steam engine in this next chapter. Okay, see you in a while. Hope your chin's okay. I've taken it on the chin quite a few times in my studies of thermodynamics.